Hello and welcome. Thank you for joining this online event today. My name is Sahina. I work as a senior engineering manager at RedHat. At RedHat, I work in the cloud storage and data services unit and primarily work on integrating storage with the container and virtualization technologies that we have. Today, I will be talking to you about storage in the open hybrid cloud and how storage can be consistent across the hybrid cloud. The key takeaways that I want to leave you with are to understand what is an open hybrid cloud and what does it mean to you to build an open hybrid cloud, the storage options that are available when we talk of a hybrid cloud, and the challenges that we commonly see. And then introduce RedHat Openshift Container Storage, do a deep dive into the technology stack, and address how OpenShift Container Storage helps overcome the challenges that we see. When we look at enterprises today, most enterprises have a cloud offering. So they start off either by building applications or new applications and providing it on the public cloud, or porting their existing application to microservices like architecture and moving it to the public cloud. But as enterprises move and start changing their existing applications, oftentimes they see that the legacy applications are not suited to the microservices architecture or cannot be easily re-architected. There are also other concerns around data privacy, the latency requirements that they have, or even data gravity for their on-premise workloads. So what we see today is there is a mix of private or on-prem offering and a public offering, or even multi-cloud offering. And this hybrid model is growing, and that's the reality that most people have this hybrid cloud and have to deal with how workloads can be migrated across the cloud. But we also see that the hybrid clouds are architected differently. When applications are built, they are not built, instead of connecting those various environments, the applications are built so that they can be portable across these environments. So the way that it is done is to have a consistent platform for the applications. So for instance, having Linux as the OS everywhere. And then building the new applications as loosely coupled services, small applications that are coupled together, that are a collection of independent services or a microservices architecture. So this is what cloud native applications are. And managing all of these applications using an orchestration engine, a container orchestration engine like Kubernetes or OpenShift. So by having this consistent platform across the environments allows the applications to move or port from one environment to another easily. And when you achieve all of this through open source software, then you have an open hybrid cloud. So an open hybrid cloud strategy brings the interoperability, the workload portability, and flexibility of open source software to enterprise environments. So now that we have established that containers and the hybrid cloud is a way for making sure that applications can be ported across. So how can storage be deployed for, persistent storage be deployed for containers? So most enterprises already have some kind of enterprise storage that they have invested in. And when they start off on this journey of containers, they want to reuse the storage that they already have rather than procuring new storage. So the first option that everyone thinks of is to provide an NFS mount to that enterprise storage array that they already have. But this has a limitation that it's not dynamic in nature. Every time the application requires storage, you need to contact the storage admin and provision storage for you. And as your application needs grow, the storage needs also grow, and you will need to raise a ticket again to provision extra storage, etc. So the whole purpose of moving to the microservice architecture and the hybrid cloud is to make sure that everything is agile and portable, etc. But when we are talking about this kind of a static model, this is not a great option. Enterprise storage companies have introduced dynamic container storage layer to overcome this. I think there are a lot of enterprise storage companies now providing a bridge to their enterprise appliances. There are also big cloud providers that provide storage on the cloud for containers running on the cloud to connect to that storage. But all these are locked into their solution. So when we talk about application portability or workload portability, how does the storage port from one environment to another? So either you are thinking of solutions at replicating storage from one to the other, or sometimes you even end up re-architecting some of the application layers that talk to storage, because storage features are different on every cloud or on-premise. There is no consistent storage layer available across these platforms. There's also the problem that you are now locked into one single vendor. So I think most storage providers, even cloud storage, are providing an on-prem option, but then you are always tied into that storage option. And in the public cloud storage, when you talk about multi-zone availability, that feature is not yet available. So if you need to run a highly available application across multiple zones, the storage, however, is tied to single zones and cannot move, or you cannot have it replicated across zones. So all of these limitations are because of the fact that storage was not built for containers, and storage is not built in with Kubernetes. Kubernetes abstracts away the infrastructure that it manages. It is very dynamic, balancing load, rescheduling, and it is defined with stateless in mind. So how do we define storage on Kubernetes the same way we define applications on Kubernetes? If we define storage in this way, it's a container native way, and storage can then move with the applications. So whenever applications go, wherever the applications can go, the storage goes with it. So what we have seen now is that the container storage needs to be simple, portable, and scalable. So simple by making use of automation to deploy and manage the storage. Simple so that developers can self-service using Kubernetes APIs that they're already familiar with. And portable across all common infrastructure environments, be it bare metal, virtual machine, or any of the public or private clouds that are out there. And it should offer the freedom of choice by not being tied to a single vendor. And lastly, the container storage needs to scale as your business needs change, and have the ability to handle the data-intensive workloads like AI, ML, and maintain the same performance as your scale grows and capacity grows. So this is where RedHat OpenShift Container Storage can be an answer, because OpenShift Container Storage works on any platform that OpenShift works on. OpenShift is Red Hat's distribution of Kubernetes, and it can work across all environments out there today. So bare metal, virtual machines, and OpenShift Container Storage can work on this platform and consume storage from the environment that it is running on. So if you're running on-prem and you have legacy storage, OpenShift Container Storage can work with it. And it provides an abstraction layer that is consistent across all of these environments without having a lock into a single vendor. So if I were to reiterate this, it is a single platform everywhere, and it provides on every environment block, file, object access, a consistent interface for applications that are running on OpenShift, on be it VMware, be it bare metal, be it any of the public cloud or private cloud offering that we have. So how is OpenShift Container Storage built? It is primarily 3 main open source projects that are combined to form this product. So we will look a little deeper into each of these 3 projects. At the core is Ceph. Ceph is an open source distributed software-defined storage. It provides block, file, and object access to applications. It is massively scalable to support petabytes of data and thousands of nodes. It can work on commodity hardware and distributes data among servers and disk. Ceph can auto-recover from any failure. So if Ceph detects a failure, it automatically rebalances and heals the data, providing resiliency and availability to your data. Ceph has a huge community following and is used by enterprises around the world. So it is an enterprise-proven software-defined storage product that is community-driven too. The next element of this whole solution is Rook. Rook is the storage operator for Kubernetes. I think Rook is the only CNCF graduated storage project of choice for Kubernetes now. Rook supports various storage backends like Ceph, MinIO, Cassandra DB, or even NFS. But Ceph continues to be the most widely used and strongest implementation for Rook. Rook automates the deployment of Ceph. So Ceph deployment is often considered complex, and Rook abstracts this away. It manages and monitors the Ceph cluster, ensures that the cluster state is as expected by the user, as defined by the user. It reconciles the current state to the desired state. And also Rook can upgrade the Ceph cluster automatically. So all of this is done without any downtime for the end user, any downtime to the storage availability. The third component in this whole solution is Nuba. And Nuba provides the consistent S3 object storage interface in OCS. So Nuba provides data management and data federation layer across multiple cloud environments and across the hybrid cloud environment. So for containers, most container storage is asked in terms of a persistent volume or as an object service. So persistent volume can be either a block request or a request for a shared file system. So both of this is provided by Rook Ceph. So block is primarily used for DB and transaction workloads where there is low latency requirement. And a shared file system is used when you already have a legacy application that is used to talking to a shared file system, or your application containers require a POSIX compliant system that they want to work with. Both of this is provided by Rook Ceph and consistent across all environments. So the same access across any of the cloud, be it AWS, Azure, IBM Cloud, or on-prem when you're running it in your data center. The other popular data access is via an object service, either via an object claim or directly using an S3 endpoint. So Nuba provides a consistent object interface across the various cloud offerings, and object is now very popular among all of the AI ML workloads. Whenever you want archiving or for storing unstructured data, and unstructured data is growing rapidly. So object is I think become very popular in the container workload space. So if we look at all of these components and how it is deployed, so OCS is a meta operator that then deploys the operator Rook and multi-cloud gateway or the Nuba operator. So the Rook operator then deploys the Ceph cluster underneath. It deploys all of the pods that are going to manage and make sure the data is replicated across the various failure domains, etc. So applications ask for a volume claim, a block, or a file. This is serviced by the CSI pods that are running on the storage nodes. So similarly, Nuba operator deploys all of the Nuba components that it needs. This is, you can specify what are the storage nodes that you want to run this storage cluster on, and also define the kind of storage that you will be providing to Ceph and to Nuba. We will look deeper into this in the coming slides. So when we look at Rook, the Rook is made of mainly the Rook, which is the operator, and it owns the management of Ceph. The CSI allows you to dynamically provision and attach storage to your client or application pods. A CSI is the interface for any storage volume in Kubernetes. It is the standard interface that all storage vendors have to implement. And Ceph is the core of this, which actually provides the data layer. It actually manages and manages the data that you are storing. So if you look at the Rook architecture, so the volume applications look for or ask for a volume, be it a block or a file. It is serviced by the CSI that is running on this. So Rook operator, like I said, is the core component, and it manages Ceph, it deploys the cluster. The operator decides how to actually place the various pods. So if it is the data pods, the object storage daemons, which I will talk about later. So it determines which are the storage nodes that it needs to provision these pods on. So Rook also deploys the CSI pods, the CSI provisioner, and the CSI node plugin pods. So any application claim is then serviced by the CSI provisioner, the CSI node plugin that runs on all the nodes in the cluster, all the nodes, not just the storage nodes, which service the storage layer. It also runs on the application worker nodes. The CSI node plugin is responsible for attaching and mounting the volumes to the application that is requesting it. So these are deployed by Rook as well. Rook deploys the Ceph cluster underneath. If we look at the Ceph cluster, at the bottom, there is the object storage daemons that I referred to before. See, the object storage daemons are responsible for actually storing the data. So Ceph, in every file, block, or object that you write to Ceph, is chunked into smaller objects, and these are distributed among the object storage daemons. So based on the policies that you define on the storage, the data is either replicated 3 times or 2 times, and they are replicated in such a way that the storage is replicated across failure domains. So when we talk about failure domains, for instance, on a cloud, you have a zone as a failure domain. So when you want an application to run across multiple zones, and if a zone goes down, you still want the application to be rescheduled on another zone and the storage available to you, then the storage has to be replicated across those zones. So Ceph makes sure that the data that you're writing to is distributed across those failure domains so that data is available in case of a failure of whatever you define as a failure domain. It could be a zone, it could be a rack in a data center, it could be even host when you're just running with a 3-host deployment. So OSDs form the bottom layer, which is interacting with the storage that is directly available to the host or the cloud or wherever you're running. On top is the monitor. Monitor provides the cluster map. So clients accessing Ceph connect to the monitor. and retrieve the map of the cluster so that they are aware how the data clients can then directly talk to the OSDs once they get this map of the data, how the cluster is is provisioned in that particular environment. So Mons are responsible for ensuring cluster state, and they keep monitoring the health of every component that is deployed there. The other daemon that is of interest is the manager daemon. The manager daemon is responsible for keeping track of runtime metrics, the current state of Ceph cluster, including storage utilization, current performance metrics, etc. It also provides a REST API that applications can connect to retrieve information about the cluster. MDS is the metadata server that provides the file system interface on Ceph. So MDS stores the metadata information on behalf of the Ceph file system. The other component that is of relevance is RGW. RGW provides object gateway to the Ceph system. So it's called a RADOS gateway. It provides an S3 compatible interface that applications can talk to. So on any Ceph cluster, you have the object access, you have the file access, and the block access as well. So the object access is provided via RGW. The file access is provided by MDS, and applications can directly connect to OSDs when they are talking to block devices. So what else do I have to explain on this slide? I think I've covered most of the Ceph architecture. So moving on. So when we talk about Rook and how it is deploying this whole cluster, Rook does this in the Kubernetes native way. So it talks to the commonly known Kubernetes constructs like deployment, pods, services, etc., to deploy the cluster. So it uses Kubernetes API, creates a custom resource definition that is available to define the storage cluster for Ceph. So once Rook deploys the cluster, it then monitors all of the daemons, makes sure that the state, it reconciles the current state to the desired state that the user has asked for. The client pods use the RBD and CephFS clients to connect to the Ceph CSI driver and provision volume dynamically and attach and mount those volumes to the client pods. So this is all done in the native Kubernetes way, where we have the pods, the storage running in pods, connecting to the available storage underneath. So again, Ceph uses persistent volume for running the OSD or the object storage daemons. So because the persistent volume is consistent across every environment, it has abstracted away the same way that Kubernetes abstracts away the infrastructure it manages. So now we talked about Rook and Ceph, and the third component in this whole solution is Nuba. So Nuba also has the Nuba core. Nuba core composed of several components that form the core of Nuba services that provide the core endpoint. It has the database that it's used to manage the data management and the policies that it has, and a storage daemon that provisions storage from whatever object storage is available to it. So Nuba operator is the pod within Kubernetes that implements the Kubernetes controller API and deploys the Nuba application. And Nuba also has a command line interface that exposes the operator as a CLI, so to create and list custom resource definitions. So when we look at Nuba Core, so Nuba Core at the top, you have the S3 API, the S3 endpoint. This is the consistent endpoint for applications across any cloud environment. And at the bottom layer, you have the actual storage that it can connect to. So be it on AWS, it could be your AWS S3 buckets or the GCP, Azure, or IBM COS on IBM. And on-prem, when you don't have an S3 object store, it can connect to the Ceph RADOS gateway and provide a consistent storage interface, an S3 API to the applications that consume it. At the middle is the all of the core or the all of the policies, the bucket policies that define how the data is placed. So you can have policies that mirror your data across multiple clouds. So these are some of the use cases that can be defined based on the Nuba policies that you can define. So with multi-cloud buckets, you can mirror your data across multiple clouds. You can have tiering, you can have hybrid buckets, or even within a data center, you can have multi-site buckets. So the options are limitless because Nuba is very flexible in the way you can define and manage these policies. And all these policies can dynamically change. But as the policies change, the application is not affected because our application is only aware of an S3 endpoint and not how the data is placed or stored. That is defined by the administrator. And it can change when you are adding a new cloud to your infrastructure. You can decide to now move that. You decide to replicate data to that new cloud as well. So, at the top, you have, if you look at the top, you have the data management, which is giving you an active data, keeping your data available, but your application agnostic from how that data is stored, how the data is structured or distributed across what locations. This is not something the applications need to worry about. They just know that the data is active whenever they are requesting for it. Nuba is flexible in the data management, that it can work with any resource, be it on-prem with any of the cloud storage offering or on-premise. All it needs is a file system or any other object interface that it can connect to. All of the data is secured and encrypted. So you have this managed by Nuba as well. There are some data efficiency layer also built into Nuba. So you have compression and inline deduplication also available. So if we look at how Nuba actually does this ingest pipeline. So when we look at this is a diagram explaining that. So we have an object that is written into the S3 endpoint. So Nuba then fragments these objects to pieces, splitting I/O into configurable chunks. So this configurable chunks and smaller chunks is for handling the dedupe context. So once these variable size are then deduped and compressed, so that you have a smaller data set to store. So the chunks are averaged at 4 MB chunks, and Nuba does a variable size dedupe or content-based chunking, and then it compresses these 4 MB chunks using a snappy compression. This is the default, but the compression is pluggable. There is a snappy and zlib that's available. So once the dedupe data is compressed and it is then encrypted, and it is stored according to the policies that you have defined for that bucket. So every bucket has policies that I referred to in the previous slide. It could be a multi-cloud bucket, so your data is then stored across AWS and maybe Azure. It could be a multi-site policy where your data can be stored across your London, New York, and Paris data center. So this is how any data that is written into Nuba goes through the pipeline and finally stored. So Nuba supports the bucket claim that is available in Kubernetes now. So bucket claim is very similar to a persistent volume claim. So when a user requests for a bucket claim, Nuba then creates a new bucket and a new account accordingly. So this application is then provided the credentials back such that applications can now use the credentials in that bucket claim to connect to that bucket and read-write data to the bucket. The policies on the bucket can be changed dynamically. So all of this can be also done via the Openshift web console. It provides a user interface for you to configure bucket policies, etc. So this is an example of how a bucket claim looks like. So you are asking for, based on the storage class name, you have requested for a bucket called OBC test. And once that bucket claim is provisioned, you are given a list of access credentials to access that bucket. And this is what applications can then use and use across multiple clouds. So now that we have seen what Openshift Container Storage is, let's look at the common use cases. So Openshift Container Storage can be used wherever you require persistent storage. So this could be at the cloud native infrastructure data services for running, for instance, Prometheus, Elasticsearch, or even your registry. Container storage can be used here. It can be used for data at rest. Any databases, the backend provides a block object storage. You can use Openshift Container Storage. It can be used for data on the move, like messaging and streaming applications, Kafka or Knative, serverless. It can be used for data in action for your AI/ML workloads, your TensorFlow, Spark, Jenkins, when you want to dynamically create your CI/CD pipelines. This is also where you can use container storage. It's not limited to what I have shown on this slide. The options are many. These are just some of the common use cases that Openshift Container Storage is used for. So I hope I have given you a little bit of introduction and understanding of how Openshift Container Storage is architected and how it can be used to solve the challenges that we commonly see with a hybrid cloud by providing a consistent data service layer and by working with any storage that is available, be it on-prem and an enterprise storage or on cloud, your EBS or your dynamic storage, with which whatever the storage, cloud storage is available on the public cloud, OCS forms a layer and also enhances the capabilities of storage, providing you consistent object, file, and block access, providing also a multi-zone availability and a data federation using the multi-cloud gateway. So this is all I have for you today. Thank you.